Hey guys, and welcome to another video in this algorithm and data structures tutorial. In this video we're going to talk about hash tables and what they are, and I'm going to show you some different kind of examples of hash tables and like what we can use them for. So first of all, we need to know what hashing is, and hash table is an abstract data structure. So in this video we're also talking about like one of the data structures there is, and in the previous video we talked about like the more basic data structures like stacks, queues, and lists. But this hashing data structure here is like it's like a data structure where you can store elements and you can have like keys pointing to the elements that you have stored. So in hashing objects, they can be fetched and stored in constant time here. So like the big O notation is OR1, so it's constant time. And then each object has a unique key in the data structure. So when we store our object in a hash table, like that object is pointed to from a unique key to that specific element. So and objects are stored in an array with the size of a prime number. So it's really important that we'll see that later on, that when we store objects in an array, like the size of the array has to be a prime number, and we're going to talk more about that in later in this video. And high performance also like requires that the objects are distributed uniformly in the array. So like they can't like be far from each other if we want like high performance in our application or in our program. And with hashing we gain like speed, but then when we gain something we also have to give up something. And in the case of hashing and using hash tables, we give up space, because often we will often like double our actual space that the data takes up. So as I wrote down here, like most implementations of hash tables requires at least like twice as much space as the actual data takes up. So in the case of hashing we give up space, but then again we like gain a lot of speed for a program, which is more like which is better for like more normal like applications and computers and stuff like that. Like we just want speed and we don't really like care that much about space anymore. So when we're talking about hash tables, we're operating with the key value pairs. So a pair has a key and then a value, as we can see down here. So when we're talking about like an object that is stored in a hash table, it has a key, and that key is pointing to the data, and then we create this key here with something called a hash function, which we're also going to talk about in this video. So as I already said, like the hash table is an abstract data structure, and it is one of the most used data structures for really large data sets, because as we talked about, like the complexity is very fast, and if we have large data sets, like we can do fast inserts and searching in our data structure. And the key value pair here, like in hash tables, the objects are represented as the key value pairs here, and then the keys are used for indexing the value and data. So the key is pointing to some data, and then the key is generated from a hashing function. We can also have, like, if we just go a step back here, we can have like the direct address table. So if we have a small number of elements that we need to store in our array or a list, then we can just say here that we have our keys that is pointing to some location in the list here, and then that index here, it corresponds to some value that is stored. But like if we get a lot of these number elements, or like really large numbers for our index, then it really takes up too much memory, and we can really like use the direct address table if we like have larger arrays. And then like in direct address tables, like no data can have the same key value. So one key corresponds to like a correlating like one data in the memory, where in hash tables, like we can have like a key that is like pointing to multiple data elements in our list or array. So if we now talk about like the hash table, then we have the key that it produces the new index for the required elements. So let's say here we have like our universe here, and then we have the keys here that like are indexes for the elements that we have stored. So in this case here we have some different kind of keys here. There is pointing to an index here in this list, and then on the indexes here we can store elements. So we're operating with this key value pair. So we create a key here with our hash function, and then that key is pointing to some location where our data can be accessed or where data is stored. And we can have different kind of hash functions, which I'll show as well later in the video. So an example here of a hash function, and a hash function is just like we have talked about, is a mechanism of placing an object in the array. So we need to like know where we should place the object, or where we should take the object from if we want to like search for it or delete it in some way. And there, like as I said, there are many different types of hash functions, but an example down here is that we have a hash function and then return the value, like where we take like the value, the hash value, and then we take the modulo of the table size. So I talked about like the table size, it has to be a prime number. So then we take the modulo and then return the rest of that operation. So first here we have our hash function here, and we give it the key here, which in this case is a string that we give it a key. And then we also have to give it the table size, so the size of the table that has to be a prime number. And then we have some local variable here and temporary variable called hash val. And then we go through the whole key here we entered in our function, and then we just add the key value from like each element on the key, on the string key, and then add that to the hash value here, and then we take the hash value and modulo with the table size, and then we return the remainder of that calculation, which will be our index to the object in the array from our hash function. But when we're using hash function, also like collisions, they can occur in hash tables, and because if let's say that we have a hash function that is producing a key like or an index that points to like multiple elements, so we can like, so there will be a collision where we try to like point to an index where we should have stored one element, but it is like pointing to an element where the element like is another element. So we can prevent this by using something called chaining, where when we point to an element here in our index, and then our index we just use a list, like a linked list or array, that our element is like a list, and if there's a collision in our hash table, we just add that element to our list or array. So let's say here, for example, we have a key here, key 3 and 4. They're both pointing to the same, like they're both hashing to the same index here, and then it is pointing to the element here. But then instead of colliding the two elements here, because these are two different elements and they're storing two different numbers of data, so there will occur a collision here if we didn't use chaining. But in this case we're using chaining, so if a key is pointing to the same element, then we just like add another element to the list here, and we just chain all the elements so collisions won't occur in our hash table. We can also use like open addressing and probing for avoiding collisions, and another like approach instead of using this chaining method here, where we can have something called like linear probing, quadratic probing, and double hashing. So I just have an example here where we're using linear probing, where we start with an empty table here, and then we add the number 89. So we add the number 89 here, and again here in this example here we use the hash function that we just went over, where we're taking like the hash value and modulo it by taking the modulo by the table size. So in this case, like all the numbers that is ending with 9 will be stored at index 9. So we first add 89 here, and it will be stored because the index here is empty, so we can just store it here. And then we add like 18 as well, and there's no element on the eighth index here, so we can also add that element. But if we try to add a new number here that ends on 9, we will get like a collision, because we can't just add it here because there is another element. And in this case we're not using chaining, and if we're using chaining, we will just like chain this 49 with 89 here in a linked list or in an array. But in this case we're using linear probing, which say that we just take the next spot that is free in the array or like in the hash table. So in this case here we just go from index 9 to index 0, and then we can then put in our element here, which is 49, And again, we try to add another element here which ends on 8, and that is already like the place is already taken here in the hash table. So we just add it again to the next next empty spot in our hash table, and so on and so forth. With 69 here, we just store it at the second index. So this is like how we do linear probing. So we just like store the values in the next free spot. And if we use, for example, let's say like quadratic probing, we will just like square all the indexes. So if we start with, for example, 1 squared and then 2 squared, so and then we give them those indexes. So let's say we use like we start with the first index here, which is 1 squared, and then we have 2 squared, which equals to 4. So then instead of like when we're using linear probing, we will just store the next element here in the second index, but when we're using quadratic probing, we will store it in the fourth index instead, which has some advantages in some cases, and we probably use like quadratic probing more than linear probing. And when we use quadratic probing, it's also here when like the prime numbers. So as I said in the start of the video, we need our hash table to the size of the hash table to be a prime number, and it is because when we're using quadratic probing and our hash table is not a prime, like the size of the hash table is not a prime number, there will be a lot of errors, and we can't store our data in a correct way, and we'll get some errors with our keys that we derive from our hash functions. So last here in our slides here is just like some applications of hash tables and when we use them. I said earlier in the video that like hash tables are one of the most used data structures when we are operating with larger data sets. So it is like using hash table is good when constant time lookup and insertion is required, and they are a lot of times and in many cases. And also if we are like doing some applications with cryptographic, they're also very useful to use hash tables, or if indexing data is required. So if we have some data that we need to index and know like what the index is, and yeah, we just use that in a lot of applications, and that is like why hash tables are such a useful data structure to know. And then just to round it off, like here we have the efficiency for hash tables and other data structures, where first of all we have the vector and list, and it has the complexity O of n. So it's a linear. It has linear complexity, where like the binary search tree here has O log of n. So it's still better to use like binary search tree over like vectors and list in this case here for efficiency. But if we're using hash tables and we can set them up in the hash table, then we get like as we just talked about up here, we get like constant time for lookup and insertion, which make it really fast. Our program if we need like applications that need speed. But again, as I said earlier in the slides here, like we gain speed, but we have to give up memory, because in a lot of cases we have to double up the memory compared to some other data structures. So we're not jumped into Sublime Text here, and I just wanted to show you the example we went over in the slides with the hash functions here, where we just took like the hash value and took the modulo of the table size here, and then the hash function here returns an index for a key, for a given key. And if we go down here to our main function, we just define a key here that is called hello, and then the table size 17, which is a prime number, and we talked about that in the slides, why it's necessary that our table size is a prime number. And then we can get the hash index, like the index for our hash function here, in a variable called hash index, and we just call the hash function here and pass the key we want to give, like we want to get an index for, and then the table size, which is the size of our hash table here. And if we print this out, we can see that in this case here we get the index 7 for a hash table. So if we want to look this element up in our hash table, or want to store this element or this key in our hash table, it will be at index 7. And we can also try to have 13 here as the table size, and then it will store it at index 6. And we can even try to change the key here and print that out, and then it will store it at hash index 1. So we give our function here a key and then the table size, and then it will calculate an index for that element in our hash table. So that's really useful, and as we talked about, there are a lot of different kind of like hash functions, but this was more like a simple one just to show you. You can look up on Google like other hash functions, and some hash functions is also more useful in some scenarios than others. The second example here I want to show you in the code is just like how to implement a hash table in C++ from like the beginning, and some of the methods that you can do on a hash table, like for example insert an item or delete an item. So we started with here, we create a class, like we used it's an abstract data structure. So first of all, we just create a class here called a hash table, and a hash table, it has a capacity, and then it has a table, and we implement the hash table here in C++ as a list. So the capacity is just like how many elements the hash table can store. And then we have some public methods here where we just have the constructor here. So we initialize our hash table here with an integer called v. And then we have these three methods here for inserting an item, deleting an item, and checking if a number is prime, which we're going to use for the size of the hash table. So to check if the number is prime, we just first of all we check if n is equal to 1 or 0, because then we know it's a prime number, and we just return 0. And then else we just run through a for loop here that it's just some math to check if the number is prime. Like we can like divide it by like take the modulo of the n numbers, like the number we entered here, to check if the number is prime, and then go through this for loop here and check if this like calculation is equal to 0. And if it's equal to 0, we just return 0, and then it's not a prime number. Or if it's a prime number and we've been through all this and we haven't returned anything yet, we just return 1, and then we can see that it's a prime number. And we can also have like a function here, like to get the prime number in some cases. If we want to like extend our array, we have to like first check like what is the next prime number. So we can use this function to like get a prime number if we want to resize it in case we're inserting an item in our hash table. And then again here we just have our hash function here, which is just the key that we take like the modulo of the capacity, so the size of the hash table, which is the other function that we just had in here in the other example. And then to the functions where we have to like create our hash table here, where we have we pass the parameter here c, and then which is like the size we want to give our hash table. So first of all, we need to check if the size is prime. So we'll get the prime number here of c, which is like the nearest prime number to the value here we enter to the function. And then we just say like the capacity for this hash table is equal to size, which is the prime number. And then we can just create a new table here with this command here, new, and then we implemented our hash table as a list here with the capacity here. So we create a new instance of a hash table with some defined capacity here. And then we have the two functions here where we can insert an element in our hash table, or we can delete an element. So in case we want to insert an element, we need to give it the key. As we just showed in the previous example, we need to give it a key where our hash function can generate an index where we have to store, where we can store the data that we enter here as the second parameter. So the index here will be our hash function, which we give it the key. So it will return some index, and then we can just say at the index in the table at this index, we just push back the data that we have given up here as a parameter. And if we want to delete an item in our hash table, we just give it the key where we want to delete that value. So it could be, for example, a name or something like that. But in this case, we give it an integer. So we want to delete some key in our hash function, or like in our hash table. And first of all, we just start with generating our index again. So in this case, we need to use the same hash function from, like if we insert an element with one hash function, we need to use the same hash function again to delete an element. or else it will just like delete some other, like it will return some other index and we will delete the false item. And then we create an iterator here that can just like go through the whole table, and then we can say like if we find like the element, like when we find the element that corresponds to like the key element, that like the index of the key we want to, then we can just go down here and say erase that element if it's found when we're going through the whole table and the index finds like the index is now where we at, then we just erase that element from the hash table and update it again. So we just have some function here to like display our hash table when we are doing some operations on it or methods. So if we go down here to the main function here, we just start with creating some key values here and then some data that we want to store in our hash table, and then the size of our hash table here. So first of all, we start with creating an object here of the hash table class, and we initialize it with the size of the hash table we want. And then we can go through here the for loop where we just insert the items from this key list here. And then we can again call like delete item. So in this case here, we want to delete, it's not the 12th index or like the data 12, like the element 12. It's the key 12, and then we have to like get an index from our hash function, and then delete that element that corresponds to this key value here. So if we just print this out, we can see that first we just store like the elements here, like data we want to store, it just gets stored here in the table, and some of the indexes here are free because we're using this hash function that just creates an index in the hash table somewhere, and because we have a prime number, everything can be stored fine. And we can see down here that we have like some elements that would collide if we didn't use this this chaining method, where we just add the elements, like at the 6th index here, we just add the elements, like we just push back the elements as we can see up here. So if we find some index or like a key map to some index where there's already data, then we just push back that data onto our table here. So and one index in our hash table can store multiple numbers of data or elements. So that's pretty much it for this video, guys. We've been over like the basic stuff about hash tables and how we can use them in code and use these like methods on them, where we can insert an item and delete an item, where we just have to give it a key value, and then that key value will be converted to an index, and then that index stores an element or the data. And we've also been talking about like why hash tables are so useful when we're dealing with large data sets, because they're really fast, but again, they also like give up a lot of space, but we don't really care about that much anymore compared to speed, when we just want our programs and applications to be as fast as possible. So yeah, thank you for watching this video, guys, and just remember to hit the subscribe button and bell notification under the video, and also like the video if you like this content and you want more of it in the future. I'm also doing right now the artificial intelligence and computer vision tutorial in C++, so if you're interested in one of those, I'll link to one of them up here, or else I'll just see you in the next video, guys. Bye for now.